Hello and welcome to Creating Geometry with VEX. Today I want to talk about creating geometry through code directly in Houdini because this is a very powerful concept that opens up a lot of possibilities for you. Of course, there are ways to generate geometry using the add node and millions of other ways, but using VEX is very flexible, and that's why I want to talk about it. But before we dive into Houdini and have a look at the code, let me quickly explain how Houdini stores geometry and what geometry is all about. So the most basic building block of geometry is the polygon. So let me quickly draw a polygon. It might look something like this, if I draw it in perspective. And this polygon is made up of 4 points, which define the corners. Let me enumerate them. This is point 0, point 1, point 2 and point 3. And all this lives in a Cartesian coordinate system with 3 dimensions. So which information does the computer have to store to be able to understand this shape? Basically, the first thing the computer has to know are the coordinates of the points. So what it does in memory, it stores a point array. Array is just a list in memory, and the list is enumerated starting with 0. In our case, we have 4 entries, 0, 1, 2, and 3. And these indices in Houdini are called ptnum, point number. And the data that is stored is basically the coordinates as a vector. So in our case, this might be something like x is 0, y is 1, and z is 0. At point 1 we have an x value of 1, y 1, 0. Point 2 might be 1, 0 and 0, and point 3 happens to sit at the origin 0, 0, 0. So this information here enables the computer to find the point in Cartesian space, project the point to the camera plane and draw it on the screen. The information that is missing is actually the connectivity information. So we want to tell the computer that point 0 is connected to point 1, point 1 is connected to point 2, point 2 to point 3, and point 3 again to point 0, closing the shape. This connectivity information is stored in the structure and is called the primitive. So in memory there will be a second array called prim array. Again, enumerated list. In our case, it only has 1 entry with the index 0. And this stores just references to the points. So basically, in our case, first comes point 0, then point 1, then point 2, and then point 3. So now the computer knows it has to start at point 0, go to point 1, then to point 2, then to point 3, and back to point 0 again. How do we tell Houdini to go back to point 0 without storing another point? Well, when we create a primitive, we not only give it the references to the points, but we have to tell which type of primitive we want to create. There are 2 types. The first is polyline, and the second one is poly. And the difference is polyline is just open, so this will just give us the edges or lines, and poly will close the polygon and give us an enclosed and filled shape. So this here, poly. Now we told Houdini the point positions and the connectivity information, but there's one other specialty we have to take into account, and this is the polygon's normal. As you probably know, every polygon has a normal, and the normal, I draw it here, is orthogonal to the plane in which the polygon lies. And this normal is defining the direction the face is facing, basically. So in this case, this is the front, and on the other side is the back. But it could be perfectly the other way around. So what if this vector would point in this direction? Then this would be the back side of the polygon. How do we tell the difference? The difference is determined by the so-called winding order. And what the winding order is just the sequence in which these point references are stored. So you can easily see that if I store another primitive, let's call it 0 star, and I store point 0, then 0.3, then 0.2, and then 0.1, it basically gives the same polygon. It's just that now we are traveling in the counterclockwise direction. You see? So basically the order the points are stored in is exactly the other way around, and this gives us the other normal and makes the polygon look into the other direction. This is pretty much everything we have to know about geometry. There is just one more thing missing, and that is the vertices. I told you that the connectivity information is just a list of references to the points. And this list is not directly stored, but instead the polygon is made up of vertices. And you can think of vertices like placeholders, basically. So if you have a polygon, this polygon has no geometric shape. It's just connectivity information. It connects this point here to this point here to this point here to this point here. But the points are not determined yet. So I have just in memory primitives, and I have a primitive entry 0, but it's empty. So these here are basically empty spots that can hold a point. And these empty spots where a point could go are the vertices. So this primitive here, and I draw it with area, but in reality it just is not existent, or it has no area so far. It just has 4 empty spots where points can go. Now I can fill in these with actual points. Let me draw them in different colors. So I can put a point here, let's say point 512, and here I put point 23, here I put point 8, and here I put point 1. Now I defined where this polygon lives. So basically now I wrote down this vertex here, now holds the reference to point 512. This vertex holds reference to 23, this is 8, and this is 1. So a vertex is basically a placeholder. And what you can do is you can create a primitive, and if you create it, it will not have any vertices. That's because you can define any number of vertices. You can add as many vertices to a polygon as you would like. So if I want to create a new polygon, what I can do is I can create polygon number 1 and say it has 3 vertices. So that means I now just prepare a structure in memory to hold 3 references to points. So I tell the computer that I will create a connectivity information for 3 points. That's why I do one primitive with 3 vertices. And now I can fill in these numbers and say, okay, this vertex here will be referencing point number 512, this will be point 8, and this will be point 1. And if I do so, what I get is 512 is connected to 8, is connected to 1, is connected to 512, in the case that I specify this to be a poly, not a polyline. So then I created this primitive. And that means that if you want to create geometry, what we have to do is first, we have to create the points. So step 1 is create points. Then we create a primitive that has to store the point references. Then we give the primitive vertices, create vertices, as many as we need points, and then D, store point refs in verts. That is the basic sequence. Here we are in Houdini. Let's put this theory to good use and create some geometry. First we need a geo node to hold all the geometry we want to create. Get rid of the file and lay down a wrangle, in this case a point wrangle. There we have it. And with Alt-E, I can open this little code editor, which makes it a little bit more convenient to code in Houdini. So at the moment, the scene is just empty. Remember what we just said, we want to first create the point. So let's have a look at the VEX functions index, and let's see which function is there to create a point. And the function is called addPoint. And here you can see addPoint needs a geo handle and then a point number, or a geo handle on the vector. What we want to do is we want to specify position, so we use this second definition of the function. Let's just copy this and switch back to Houdini. So I paste this here. It's telling me it's returning an int. That is because this function is creating a point and it's giving back to me the index of this point. So I have to create a variable. In this case, I call it pnt for point 0. Will be the index that is returned by the function addPoint. The first thing we have to specify is a geohandle, and that is basically the geometry we want to create the point in. This is referring to the inputs of this point wrangle. In our case, we want to create the geometry just in input number 0. And then, last but not least, we need a vector, and this vector is specified with curly brackets. And in our case, let's create a point at the origin, so 0, 0, 0. And don't forget to terminate the line with a semicolon. If we now press apply and accept, we see no errors, but we don't see a point, unfortunately. Even if we switch on point display, there is no point. And middle click on the node makes sure there is really no point. This is due to the execution of VEX. This point wrangle here, and you can see this here in this parameter, is running over the points of the incoming geometry. But as there is no geometry, and no geometry of course has no points, the point wrangle is not executing. And because it's not executing, it's not adding a point. So what we could do is just add some points in, but then we would have the points that are coming in plus the point we are adding. That is not what we want. Instead, what we can do is we can switch this here to detail only once. What this is doing is it's actually executing this code without any input geometry. And now you see, as soon as I switched, I have this point here. Let me turn on point numbers and you can see the point here. If I quickly go to geometry, I can maybe just increase the point size and you can see it here sitting at the origin. So our very first step to creating geometry has been successful. Now it's time, and let me open the code editor again, to create more points. Let's stick to the example we had a second ago and create 4 points. So I copy this line, paste it 4 times, and just change the variables. So this will be point 1, this will be point 2, this will be point 3. And of course the coordinates. So point 1 will be here, point 2 will be the upper right corner, and point 3 will just be like this. Let's apply this and accept. And you see that you have 4 points now. 0, 1, 2, and 3. So the first step has been done. Now remember the sequence I told you earlier. The next thing will be that we want to create a primitive. So let's switch back to the index and see which function is there to create a primitive. As the first function for adding points is called addPoint, chances are that the primitive function will start with add2, and it's true, here it is, addPrim. So addPrim is again expecting a geohandle and a type, because this is just creating the connectivity information, if you remember. So let me again copy this, switch back to Houdini, and paste it here. This addPrim function is again returning an int, and this is because it's returning the index of the polygon for the polygon array. So let's create a variable to store this index. I call it prim0. And prim0 add the prim, again in geometry. Input 0. And now we want to specify the type. And this type is the information if this is a polyline or a closed polygon, in which case I write down poly. This is a string parameter, that's why I put it in parentheses. Terminate the line with a semicolon, hit apply and accept. You don't see anything yet, because as I told you, there are no vertices, so this primitive is there, it's just empty. We can make sure that it is there by switching to the geometry spreadsheet. In the geometry spreadsheet you have the point array visible here under this first tab, where you see our 4 points and the coordinates. If you switch to primitives, you see that we actually have one empty primitive, but it's not storing any points yet. That's why you cannot see it. So let's change this situation by adding some vertices. Again, we switch to the index, which is your best friend while coding VEX, and search again for add. And here you have add vertex. Add vertex will add a vertex. It is expecting a geohandle, and now two more parameters, of course, because it's expecting that you tell it which primitive to store the vertex in and which point to reference inside of the vertex. So this time copy this, switch back to Houdini, and let's add 4 vertices. The vertex is returning a linear vertex number that can be used to address the vertex later. It's not necessary that you store this, but you can if you like. So let's call this vertex 1 or vertex 0 to be consistent. Is add vertex. Geohandle is again 0 because we are operating on the geometry of the first input, or the first geometry that there is. The primitive is now the primitive ID we generated earlier, because this is a primitive we want to add vertices to. And the point we want to add is the first point, so we use this variable that is storing the ID of the first point. Now we created 1 vertex inside of this prim. Let's duplicate this line 3 more times to in total have 4 vertices, and change the information to vertex 1, vertex 2, vertex 3. The primitive will always be the same, but the point will change. The first vertex is referring point 0, which is this. The second one is referring point 1 here. Then comes point 2, and then comes point 3. And now if we hit apply and everything works out, look what happens. There it is, our first primitive. And you can verify this information by again switching to the geometry spreadsheet. Now we have this primitive here, and we have vertices. These 4 vertices, you see here, these vertices are belonging to the 0th primitive, that's the first number, and then comes the linear vertex number, which is 0, 1, 2, and 3. And here you have the point indices these vertices are referencing. So you can see the first vertex of the 0th primitive is referencing point 0, which is this here, and these coordinates. And there you have it. This is necessary to create a polygon in Houdini with VEX. But now for something a little bit more interesting. I downloaded this nymph here from the internet. It's actually a 3D scan that I optimized a little bit in ZBrush and imported and scaled down here to Houdini. It is from this excellent site here called 3D Scans, which is a project by Oliver Larridge. And he provides a lot of scans of fine arts for free, actually, and even some animals and stuff. It's an excellent source if you need nice geometry to work on. So I recommend to check it out. What I want to do here to generate an interesting structure is to scatter a lot of points on the surface of this nymph and then connect these by proximity. So I want to basically go through all the points, find the closest neighbors, and connect these with polylines, which gives us an interesting structure known by plugins like Plexus for After Effects, for example. So the first thing we want to do is lay down a scatter node and just scatter points on the surface of this nymph. Maybe some more. Let's do 2000. And in this particular case, the very nice function of relax that makes sure that these points are evenly spaced is not so good, because we want a little bit of irregularity to make the structure more interesting. So turn off the relax iterations. That leaves us with some more randomly distributed points. Now that we have the points, what we have to do is put down, again, a point wrangle, which will be used to create the polylines. Okay, open the code editor by pressing Alt-E. Before we can start adding geometry, we have to make sure to find the neighboring points. What I want to do is, for this point here, for example, I will find all the points in a certain proximity and connect these. So I will need a VEX function to find these points, and fortunately there is one. It's called near points. This near points function is returning an array of point numbers, so of point indices, around a search point or a search position. So let's copy this definition of the function over to Houdini and paste it in here. This function is returning an array, and I can tell that it's doing so because of these square brackets. It's returning an integer, but not a single integer, but an array. The square brackets tell me this. So I want to create an array variable, and I can do so by just creating a variable. In my case, I call it near pnts. That is directly followed by these square brackets. That makes a difference to a normal variable. Then comes the equal sign to assign to it the return value of the near points function. And the near points function wants a geometry string, which can be replaced by just the input number, in our case 0. This is the incoming point. And then it wants a point, so a position to search for, or to search from. In our case, this is the position of the currently processed point. As you know, the wrangle runs over all the points, so it's basically a loop going through all the points in the geometry. And the position of the current point can be found by using the attribute p. So at and capital P will give us the position. And then there is this max distance, which is basically the search radius. That is the distance around the point that Houdini is looking for neighbors. In my case, I just put 0.1 here for now. Press apply, nothing happens. That's because now we have an array of points in memory, but we did not do something with them yet. What we want to do now is, we have an array for every single point containing all the neighbors. So to make use of this information, what we have to do is we have to create another loop to run through all of these resulting points. And as I have an array, I can, instead of using a for loop, use the more convenient for each loop. So for each, and then in the brackets what you want to put is first a variable to hold the currently processed point in the loop. In my case I call it point. You can call it whatever you like. In my case I call it point because it is a point index. Then comes the semicolon, and then comes the array, in our case near points, that the loop should run over. So this is basically a shorter version of a for loop. It just takes this near points array and then goes through all the points it finds in the array. And it stores in every iteration the currently processed point into the variable point, such that you can use it inside of the loop. Now, curly brackets. And everything that is inside of these curly brackets will be executed in every iteration. What do I want to do in this iteration? I want to create a line. So let's create first a variable to store the resulting index. Call it line because it's representing a line. And then remember from what we did previously, add prim, which geometry, 0, comma, and then the type of the prim we want to create. In our case, it's polyline. Now we have a empty polyline. It's not showing even if we press apply. Let me quickly do so. Because it's just empty. We have no vertices yet. So what we want to do now is we want to add 2 vertices to this line, because we want to create one line from every point that is processed by the wrangle to every point in the near points array. So add vertex, and in this case I skip the storage of the resulting linear vertex number because I don't need it. Add vertex to geometry 0, primitive number line, and the point number that I want to add to the vertex is first the number of the point currently processed by the wrangle, and this can be accessed with the attribute ptnum. This is referring to the number of the point that is currently processed, not by the for each loop, but by the wrangle. And the second point will be the point currently processed by the for each loop. So we add another vertex to geometry 0 and to the primitive line. But this time the point ID is no longer ptnum, but it is actually pnt, because pnt is a variable that stores the currently processed point by the for each loop. And now that we did this, what we can do is hit apply, and what you immediately see is, look at this, Houdini created a huge amount of lines pretty much instantly. The thing is that it's creating too many lines to be beautiful. We want to narrow down the search radius. And of course we can go in there and change it in code, like, for example, if I put 0.01 here, I have only very few lines, but that's not very practical. It would be great to have a slider to adjust this value. So why don't we just create a slider? What we can do is, the standard way of doing this is to go to this menu here and edit the parameter interface, create a slider, and then reference it inside of the code. But since I assume Houdini 14, there is this little button here that makes the process a lot more convenient. So just create a new variable of type float, call it search rad, for example, and make it reference a slider that is not there yet. So channel expression and then search rad. The slider should be called the same as the variable. Now that I did this, I in theory can use this variable to drive this value. So replace this by search rad. It's just, if I press apply, all the lines are gone because there is no slider here specifying the value. But if I now press this little button, what it does, it goes through the code, and whenever it finds a channel expression, it automatically creates a matching slider, in this case called search rad. And what I can do now is I can interactively adjust the search radius, and by doing so, the amount of lines that are created. Quite cool. And this is it basically for the geometry creation. It's quite simple and very flexible, because I could in theory vary the search radius for every executed point, or I could take into account different conditions, stuff like that. But there is one thing we missed out, and that is, if we turn on primitive numbers, you see a huge amount of primitive numbers, and if we go very close, you see that every line has a primitive number. But not only that, but on every point there is a primitive number too. And that should not be there. And this is due to the fact that the near points function is returning every point that is inside of the search radius. And that means it's returning a reference to the point currently processed to. So there is a line connecting the point with itself, and we don't want that. We, of course, because we want to work optimal, we don't want to have infinitely small lines in here. And it's easy to fix that. Open the code editor again. It's just that this for each loop is going through all the results that are stored in near points in this array. And the very first one is the process point. So let's do an if clause and just check for this. So let's say only add a line if the currently processed point inside of the loop is not the same as the currently processed point in the wrangle. So I write down if, brackets, if the currently processed point pnt is not the same as ptnum, and open curly brackets, only then execute these 3 lines of geometry creation. And before I press apply, let's check. At the moment we have 30,782 primitives. If I now press apply and accept, we are left with 28,782 primitives. So now no visual difference, but it's more optimal because we are not creating these very, very tiny lines. And now to finish this off, let's give these lines a little bit of color. I prefer to do this in a VOP. I could have done it in a wrangle too, but doing stuff like colorizing, I prefer to do in a VOP. It's basically creating VEX in the background, so it's basically the same. So what I want to do is I want to use a noise, so put down an anti-alias noise. And I want to use this noise to generate a color, and then just lay down a ramp parameter and connect the output to CD, like so. And probably we want to promote the frequency of the noise to be able to adjust it. If I now go up, I see on the colorize I have this gradient here, and I can adjust it to something to my liking, like so maybe. And then I can go in there and up the frequency of the noise, like so. But you see, it's not getting blue anywhere. It's only red, and there's a little bit of pinkish tint in here. And that's due to the fact that the noise node is generating values that are negative. It's not only generating values between 0 and 1, but it's generating values in the negative range too. So let's put down a fit to fix this and promote the very first parameters to be able to fix it interactively. And if we now go down here, we can just go down with this first value until we reach something usable, like probably so. This might be the range between minus 0.3 and 0.3, where it actually generates values. And now, yeah, look, now we have the control over where the stuff should be red and where it should be blue. And you, of course, can get very fancy with this, but for the moment it should do. Maybe change this to green, because I prefer green. So thank you very much for watching. I had fun doing this tutorial. I hope you have fun watching this tutorial and you got a good first insight in geometry creation in Houdini. It can be used for so many things, quite more complex things than just adding these polylines, but even that is very useful in many cases. So see you next time on this channel. And I would love to hear from you what you think about the tutorial, if the level was right, or if you want more in-depth information, or have everything told quicker. Please let me know through the comments.